everyone, my name is Josh Dillon. I'm a research scientist at UC Berkeley, and today I'm going to be talking about high-redshift 21 centimeter cosmology. Now, before I get started, I just wanted to thank the organizers of Cosmology from Home for all the work they've been putting in and for putting together this really lovely conference. So, 21 centimeter cosmology starts with something of a cheeky question, which is, how can we map out our entire universe? And when we think about making maps of the entire universe, we often think about the cosmic microwave background as this, the full extent of our observable universe. But really, what we're seeing in the cosmic microwave background is a thin shell at redshift of about 1100. And likewise, when we think about making giant maps of the universe, we sometimes think about galaxy surveys. But here, putting it to scale in co-moving coordinates, galaxy surveys like the Sun Digital Sky Survey are a relatively small fraction of the total volume in co-moving coordinates of our universe. And that's where 21 centimeter comes in. So with the 21 centimeter line of neutral hydrogen, which is the transition from the spin triplet to the spin singlet state, you get an emission of a 21 centimeter photon, which then comes to us redshifted by, say, a factor of 10. And using that redshift, if you know that a photon came from the early universe from hydrogen, then you could figure out exactly how long ago it came from. So you can use that to do tomographic measurements of, in principle, almost the entire volume of the observable universe. And in particular, there's a fraction of the universe at redshift greater than about 6, where we're using, or we should be able to use 21 centimeter tomography, 21 centimeter cosmology to make maps of the universe as it undergoes a rather dramatic transformation. So as we know, very early on, the universe was much hotter on average, but also much more homogeneous and isotropic. And the inhomogeneities were sort of at a 1 part in 10 to the 5 level, and eventually those inhomogeneities became our modern galaxies, and the universe became very much colder, but also much more complicated. And in between there's a process which we don't have a ton of direct observations of, where we think first the matter was collapsing under these overdensities during the cosmic dark ages, and eventually this will lead to the formation of the first stars, though we don't know precisely when. Those will collapse perhaps and become some of the first black holes and compact objects, which will eventually lead to the first galaxies that will reionize the intergalactic medium, and this is that epoch of reionization. And together, we call this process the cosmic dawn, which I think is a rather poetic way of thinking about how the universe went from the cosmic microwave background to what kind of things we see today. And we do have some clues about that last bit, about the epoch of reionization. So one thing we know is that it ends at roughly redshift of 6. And we know that because we can look at quasar spectra. And what we see is absorption from Lyman alpha photons by neutral hydrogen. It doesn't take very much neutral hydrogen, so it's really only probing the very tail end of reionization. But we can see that by redshift 6, most of that Lyman alpha is absorbed, and so we know that there at least is some neutral hydrogen still there. And likewise, we can look at the cosmic microwave background, and specifically the fluctuations and its polarization, and we can learn something about reionization using the parameter tau. So those fluctuations are damped out by a factor e to the minus tau, which is the optical depth to reionization. It's the total electron content between us and the CMB. And so we can say something about, rough timing of reionization. But with these kinds of clues, we can start to put together a picture of what we think reionization looked like, and we think it looks something like this. You had those first stars and galaxies turning on, and they are eventually emitting ultraviolet radiation that's ionizing bubbles. And we have this kind of inside-out growth of ionized structure until eventually the entire intergalactic medium is ionized. And from the perspective of 21 centimeter, what we're measuring is the 21 centimeter brightness temperature, which is a relative temperature compared to, generally speaking, the CMB. And it tells us about the overdensity of hydrogen. It tells us about the spin temperature of hydrogen, which is the relative fraction of hydrogen in the spin triplet and spin singlet states, and then it tells us about the neutral fraction. And we can think about these different elements that go into the physics of 21 centimeter as roughly mapping to the different ages of the universe that we're interested in. So the dark ages is a time where there's growth of density fluctuations. The first stars and the first black holes will primarily affect that spin temperature by, for example, X-ray heating the gas in the intergalactic medium. And then finally, the epoch of reionization, true to its name, is primarily visible through the ionization fluctuations and the effect on the ionization in the intergalactic medium. And there's a lot of interesting open astrophysical questions about all this. So we don't know that much about what the first stars look like, how and when did they form, how massive were they, things like that. And we also don't know that much about the process by which they die. Do they become the progenitors of LIGO black holes, or are they the seeds of the supermassive black holes, which seem to grow quite quickly early on in ways that we don't fully understand? And likewise, the intergalactic medium itself is interesting, especially because its thermal history is affected by all of this, and it's something that we could probe with 21 centimeter. But also, if anything else is affecting the thermal history of the intergalactic medium besides standard star formation processes, that would be very interesting. And this is a time when the universe can act like a thermometer. And finally, we don't know that much about what reionized the universe and precisely when that happened, and that's of interest to the broader astrophysical and cosmological communities as well. And I'll point out, since this is a cosmology group here, that the cosmic dawn in co-moving coordinates represents something like half the total volume of the observable universe. So there's a huge statistical power in learning about what's going on during this period. And that'd be great if we could make, say, 3D maps of this whole process, which in principle is possible, but it's going to be very challenging. And for a number of reasons, which I'll lay out in this talk. But I think because of that challenge, the first detection we expect to be statistical. So we can do simulations like this showing how the fluctuations and the global and the total signal vary as a function of position on the sky and as a function of redshift. And there are two statistics that are generally computed. One is the global signal, which is just the total sky average 21 centimeter signal, and the other is the power spectrum, which is the amplitude of fluctuations on different spatial scales. And those are both very interesting and can code different parts of the physics, but together they could tell us a lot. And in trying to measure the global signal, there was this little experiment called EDGES, which many of you have probably heard of, which is literally a single dipole sitting out in the desert in Western Australia. And they went out to try to measure the global signal, this dip here, and they measured something rather unexpected. Something much, much stronger, an absorption feature in 21 centimeter, much stronger than anyone expected. And there's a few possibilities for what that could be, but the only way to get a really strong absorption signal is by modifying this term, which involves the spin temperature. So one way is to make the spin temperature colder than anyone would have expected, colder even than adiabatic cooling from recombination. And the only thing around that's colder than the baryons that set the spin temperature is dark matter. So in these models, dark matter is somehow interacting with baryons and cooling it down, which would be, an incredible discovery if it turns out to be true. Another possibility is that it's not actually the CMB that is the backlight for 21 centimeter, but there's some other radiation field, maybe from radioloud quasars, though that is difficult to produce theoretically. But that's another possible explanation. And then, of course, edges could be wrong. It could be seeing some systematic, and edges themselves admit that there are they've checked many systematics, but they don't know that they've checked all of them. So there's been a lot of discussion about that. But I'll note, if it is dark matter, which would be really, really exciting, this is something that you should also be able to measure in the power spectrum at roughly redshift 17. So, for example, if dark matter has a small fractional charge, that should then imprint a fluctuation power spectrum due to the relative velocity of baryons and dark matter that we should be really blindingly obvious in the power spectrum. So the power spectrum is a way to go at this. Now, the other way to go at it is, of course, to try to repeat the measurement, which is precisely what Saros did. So this is Saros 3 experiment, which instead of sitting on the desert, sat on a lake in the Himalayas, but with a very similar kind of approach with some different approaches to systematics. They go out and they measure a spectrum, and then they subtract some model of foregrounds, which I'll come back to. But basically what they see is nothing. So after they take out their foreground model, they're not seeing anything that looks like the EDGES signal. So they are saying that they're ruling out the EDGES best fit model at roughly 95% confidence, but there's some caveats. The EDGES best fit model is not a physically motivated one. It's just a phenomenological model. It's not, it minimizes chi-squared, but that's really all it has going for it. And of course, that's just the best fit model. There's a range of parameters within the sort of 2 sigma error bars, which are not ruled out with as much confidence. So there's still some daylight here, but there is certainly some tension. And the other thing to point out is that Saros is measuring only a subset of the EDGES band, and as a result, they're only really able to see one of these turns in the supposed EDGES signal, not both of them, which I think also gives them a little bit less lever arm to mitigate the foreground. So I think this is still an open question, but certainly Saros is a knock against what EDGES claims to have seen. So I think that gives some sense of the fact that measuring the global signal is quite challenging. So maybe we should be talking about the power spectrum. And to measure the power spectrum, you need quite a different instrument. And there's been a whole class of interferometers, which are not just one dipole sitting in the desert, but many, many dipoles combined together that have sort of gotten us started. And these have been taking very different approaches. They look different, they functioned in different ways, and this is just a handful of them that have been built across the world to do this and other science. And over the last decade or so, the power spectrum limits, the brightest that power spectrum could be, have been steadily coming down as we've been getting better at understanding our systematics, and different telescopes are slowly pushing down our limits on what we can understand. And we're still a ways away from the sort of vanilla theoretical signals, but you are able to rule out the strongest possible cosmological signals. But the challenge of all of these is in part sensitivity. So we do what we always do in astronomy, which is when we need a more sensitive telescope, we just go bigger. And that was the motivation behind this telescope, which we are building and have built in the Karoo Desert of South Africa, one of the most radio quiet sites on the planet. And this giant hexagon on the desert is this. It's HERA, the Hydrogen Epoch of Reionization Array, which is the telescope that I work on. And I'm going to give a somewhat biased view of the field. This is really the HERA perspective, but of course there are others in 21 centimeter cosmology. So HERA is a collaboration led by UC Berkeley, but with schools all around and institutions all around the country, and the UK and Canada and South Africa. And of course, we're funded by the National Science Foundation and the Gordon Benning Moore Foundation, to whom we are very grateful. So HERA is made up of 350 of these dishes that are each 14 meters in diameter, and it's huge. It is the size, roughly speaking, that Arecibo was, but it's a full interferometer, not just a single dish. And because we're observing at 21 centimeter wavelengths redshifted by, say, a factor of 10, we're talking about 2 meter wavelengths. And at 2 meters, chicken wire mesh is a mirror. So we're building our parabolas out of PVC pipe and telephone poles and chicken wire mesh to observe the signal. And the complicated part is not the dishes themselves, it's all of the back end, the digital electronics, the analysis, and so forth. So because it's a relatively physically simple thing, it's just dishes that point straight up, HERA is what we call a drift scan instrument. So we're watching the sky go overhead. We observe a constant declination, plus or minus a few degrees, and that's really the portion of the sky we observe. But cosmology is a statistical discipline, and where the signal should be isotropic on large scales, so that's totally fine that we can't see the whole sky for now. We won't be able to map out the full volume of the universe, but we weren't quite at that point anyway. Now, the biggest challenge for 21 centimeter cosmology, as I alluded to before, is foregrounds. It's astrophysical foregrounds, synchrotron, and free emission from our galaxy and other galaxies. So between the hydrogen in the early universe that's undergoing reionization and all of the exciting astrophysics of the high-redshift universe, we have our galaxy, other galaxies that are all emitting synchrotron and free foregrounds that are something like 4 to 5 orders of magnitude brighter than the signal we're looking for. So different. The advantage here, though, is that those things are fundamentally spectrally smooth processes. If you know the synchrotron emission at one frequency, you know it pretty well at the next frequency. But different frequencies for 21 centimeter emission map to different redshifts and therefore different distances and really different spatially separated parts of the universe. So the 21 centimeter signal should have complicated spectral structure on many scales, and the synchrotron foregrounds should not. And that's the key to their separability, though in practice that's obviously a little more challenging. So instead of thinking about the power spectrum as reionization evolves as some power level of fluctuations as a function of spatial scale, we take our spatial scale k and we unfold it. So instead of k, we think about k perpendicular modes, perpendicular line of sight, Fourier modes, and k parallel, the Fourier modes along the line of sight. When we look in that space, we find what we call the window. And to understand the window, it's helpful to think about the following. So physically, from an instrumental perspective, the left and right side here are set by the angular extent, the field of view, and the angular resolution. It tells us the finest and largest modes that we can measure perpendicular line of sight. And likewise, the lowest k-parallel modes are set by the foregrounds. Those are completely dominated by the very smooth synchrotron emission, and the top here is set by our frequency resolution. But there's also this other effect, which we call the wedge, which is really important for understanding how instruments are designed and ought to be designed. And to understand the wedge, we need to back up a little bit and ask the question, what does HERA actually measure? And to understand that, we're going to talk a little bit about the fundamentals of interferometry. So each of these 350 dishes is just looking straight up and has a roughly 10-degree field of view, so roughly 100 square degrees, if you want to think about it that way. And that each of those dishes is not what we're actually fundamentally measuring. We're not measuring one signal from each dish. We're measuring one signal from every pair. So interferometers measure Fourier modes on the sky, which we call visibilities. And a visibility is given by the integral of that beam, that 10 degrees on the sky, times a Fourier mode, which importantly is both baseline, meaning the vector separation between the two antennas, and frequency dependent. And so what we're really measuring is something like an interference pattern on the sky. We're looking at something that kind of looks like this. And here the interference pattern is going out, but electromagnetism is time reversal, obeys time reversal symmetry, so you could also think about it as an interference pattern coming in. So shorter baselines are measuring the lazier modes on the sky. They have they don't phase wrap quite as frequently in frequency or position, depending on how you want to think about this, exponential. And likewise, longer baselines measure the faster varying modes on the sky. So one way to think about the modes that are being measured is really the K perpendicular is effectively baseline length. And likewise, what we're measuring when we're measuring K parallel, because frequency maps to distance, so closer is bluer and further is redder. If you Fourier transform distance, you get K parallel, and if you Fourier transform frequency, you get time delay. So really, you can think about K parallel and K perpendicular, the space which we want to make our measurements, is very closely associated with baseline length and time delay. And the wedge, or the distinction between the window and the wedge, is set by the maximum possible time delay for a given baseline length, which is just the speed of light, the baseline length divided by the speed of light. And that's what sets the separation between the window and the wedge, and what tells you that the longer baselines are going to have more frequency structure. They're going to be more chromatic. So our basic approach is the following. If we are working just outside the wedge, we are what I would call, this is a philosophy of managed ignorance. We don't understand precisely what the instrument is doing, but we're going to work in the regions where the instrument is having the least effect, where it's cleanest, and that's where we think we can get the most bang for the buck, so to speak. Of course, that is not the only approach, and I should be at least a little bit fair to some of our competitors. So telescopes like the MWA in Western Australia and LOFAR in the Netherlands have taken a pretty fundamentally different approach. So they are building telescopes that are not maximally compact like HERA, where we're focusing all the sensitivity on the least chromatic modes, but instead they're spread out and these have these complicated array patterns that are designed to do a better job of imaging and then directly subtracting the foregrounds as you model them. And I should mention as well that the square kilometer array, which is going to be built in Western Australia as well, is taking the same basic approach. You're building a very complicated elements and building a lot of them in a semi-random array pattern, and you're not trying to pack things in, you're trying to be a really good map-making telescope. And to do then the kind of 21 centimeter cosmology you want to do, and here's an example from LOFAR, you're going to need to have very precise models of both your sky and your instrument in order to then subtract off the foregrounds as best you can, because there's thousands and thousands and thousands of very bright foregrounds in your field of view that are way brighter than the signal you're looking for. And if you want to do that measurement, you're going to have to use some kind of subtraction. And even then, after all of that, they're still doing some kind of high pass filtering to get out the sort of most chromatic terms. Now, neither foreground avoidance nor foreground subtraction work if you can't calibrate the instrument. And this is an important point, that every antenna matters as well. So the visibility, the true visibility on the sky depends just on the separation of antennas, but the observed visibility is multiplied by a complex and frequency-dependent gain for each antenna involved. So even though we have two pairs of antennas that are measuring the same thing, they're supposed to be the same separation, they aren't necessarily measuring the same quantities if we don't calibrate them. Now, the traditional way to approach this in an imaging and therefore foreground subtraction-based regime is to do the following. You take your gains and you parameterize them by some delta so that you can linearize these terms. You drop the second order terms. You have some model of the sky. You use that to solve for your gains. You update that until it converges. Then you make an image. You find the source. You find the sources. You build a model of your sky that is deeper and deeper. You then go back and forth. You use that updated model to find updated gains and so on, and you go do this iterative what's called self-calibration. And the challenge here is what happens when our sky model is slightly wrong, because our sky model is extremely complicated and there's lots of sources in the sky, and it's often hard to tell point sources from side lobes of point sources. In particular, if you have a lot of point sources that are below the confusion limit, so they're basically the side lobes, you can't tell the point sources from side lobes. If you take those, as Nicole Berry showed several years ago now, those will create chromatic errors in your model visibilities that you're using to calibrate, which will then lead to spectral structure in the gains themselves. And in particular, what I and collaborators showed a few years ago was that the structure in the gains is set by the longest baseline involved. Because the longest baseline is the most chromatic. If you have errors there, that will create chromatic errors in all your gains, and you turn the wedge into a brick. You basically add spectral structure to a thing that was spectrally quite smooth, and now more and more of the space that you wanted to operate in is impossible to operate in. So that's there are ways of mitigating this effect. I'll talk about one in a minute, but that's something that the kind of subtlety that one needs to be aware of when approaching problems like this. So HERA was designed quite differently. It was designed to use the internal consistency of redundant baselines. So the pair in green or the pair in pink here, for example, are measuring the exact same modes on the sky, and therefore the visibility should be the same, but of course they're not because of the gain. So without using any kind of sky or instrument model, what we do is we say, okay, we have, say, 320 antennas in the core of HERA, which gives us 1,500 unique visibilities because we've measured the same visibility over and over and over. There are 51,000 total measurements, but many fewer free parameters. So it's a giant overdetermined system of equations, and the goal is just minimize chi-squared. We want to solve for our gains and our unique visibilities simultaneously in order to calibrate. And now that's not a perfect thing either. So a project led by my former undergrad, Naomi O'Rose, looked at this particularly in the context of a simulation and asked the question, well, instead of model errors, what happens if you have non-redundancy? If your array is not quite perfectly redundant, if you put in position errors and beam errors and antenna-to-antenna variation. And she saw basically the same effect, where the wedge became a brick again because of this chromaticity. But because we sort of knew the underlying physics, one thing, or really the calibration underlying this, the one thing we could do to address this problem is just not use the longest baselines, those that had the most chromaticity, the most spectral structure, and just doing that actually gets us back most of the Fourier space we were interested in. So that was one approach. There are several, and I'd be happy to answer questions about this, but the basic idea is that you have to be very careful about these sorts of things when you're doing both sky-based or redundant calibration. But I can say, in the context of HERA, redundant calibration seems to be doing pretty well so far. So we start with a bunch of visibilities here. I'm showing, the visibilities are complex, so I'm showing the angle. And here I'm showing them as a function of time and frequency for 15 different baselines. It should be measuring the same thing, and they are not. So first we got to flag an antenna 50 here, which never worked. And then we impose that redundancy constraint. So these things look totally different now, but as soon as we impose that constraint, all of a sudden they're starting to really line up quite nicely. So then we flag out some band edges and radio frequency interference, which is a whole other topic. And we fix to an absolute sky reference. So there are still a few modes that we can't solve for purely with internal degrees of freedom. We do actually have to make maps and compare them to the sky and try to calibrate the last few degrees of freedom in there. But this seems to be working quite well. So we can then take our data from a single night, and because the 21 centimeter cosmology signal is not changing from day to day, we can start integrating down. And it really seems like things are integrating down like noise up to a point. So as things are integrating down, we start forming power spectra. We're measuring just a single baseline, so it's a function of k parallel or delay. And as you start to integrate down, you start to see something appear here at roughly k parallel of 0.5 H inverse megaparsecs. And so something is sticking up way above the noise. It's not just foregrounds. And what this was something that was pretty clearly a problem that when Nick Kern, who led some of this analysis, was a former graduate student at Berkeley and now is a Papalardo fellow at MIT. And what he saw was that these systematics were contributing basically on every baseline. And it was not an antenna-dependent effect. This was truly a baseline-dependent systematic. To understand it, it was useful to not look just in the space of time versus k-parallel or time versus delay, but instead to take the visibility and Fourier transform it one more time. So to look instead at the Fourier transform of time, which we call fringe rate. And what we saw was that these terms that were due to the systematics terms, which were quite bright and really a problem for our analysis, all lived in a sliver of the space right around fringe rate of 0, Whereas the sky signal that we're interested in, including where we expect the 21 centimeter signal to be, is at a higher or lower fringe rate depending on the baseline. So this gives us the basis for separating the two. And of course, he wrote a whole paper about this, but the basic idea is that you can model that and then relatively losslessly subtract the systematics, and we get that basically back to the thermal noise limit. So with those high delay systematics mitigated, we could finally form our 2D power spectrum. We can look at our wedges, and things are looking pretty good. So outside of the region of Fourier space that we expect to be foreground dominated, which is the wedge, plus a little bit of buffer for intrinsic chromaticity and other sort of dynamic range issues, things are looking like they're pretty much noise dominated. That the signal to noise, because we're taking cross power spectra at interleaved times, seem to go between 1 and -1, which is exactly where we expect them. And we can see that roughly half of the space is negative, again, as we expect. So it looks like things are going quite well, and then we can just take the modes outside the wedge. This is that robust foreground avoidance technique, and we can form our first power spectra. So we've integrated down quite far, and we can set a upper limit. We don't think that anything that here that looks like a detection is likely systematics, not 21 centimeter signal, but we can say now with quite high confidence that the signal can't be any higher than this at this particular K mode, and in this case at redshift 7.9. So we can finally put ourselves on the big board, so to speak. We can set our first upper limits, which are actually world-leading upper limits, with just 18 nights of data and just this very conservative, minimizing any kind of losses or biases, foreground avoidance technique. And to make sure that we really believe what we're claiming, we also went through an exercise of building confidence in our results by doing a full end-to-end simulation. So we took our data analysis pipeline, and we applied it to completely synthetic data, which had sort of a boosted EOR model in it and foregrounds and various systematics, and we threw that all together. And this was work actually led by another former Berkeley undergrad, Bobby Pasqua, who's now doing his PhD at McGill. And throwing that all together, we were able to build a model of the instrument that really looked quite faithful, that had the kinds of systematics that we were seeing. We put them in, we run it through our full analysis pipeline all the way to the power spectrum, and we see that we are recovering the power spectrum that we put in quite nicely. So we can see a clear separation between the low K modes that are foreground dominated, sort of the middle K modes that are EOR quote-unquote detections, and the modes that appear to be noise dominated. And so we're really seeing good evidence that we can understand our pipeline all the way through, that we get back what we put in, and that we are not introducing any sort of unknowns, new biases, or signal loss that are affecting the astrophysical claims that we can make. So with that confidence, then we can take our upper limits and we can send them through the entire statistical machinery of a variety of astrophysical models that then we can use to interpret what's going on. In particular, we employed the 21 cm MC, which is built on 21 centimeter fast, which is a technique for interpreting in a Bayesian context a variety of parameters. So we did this whole big triangle plot, and I won't bore you with the details of that, but I wanted to highlight a few specific results. So one of the results is that at greater than 95% confidence, we can say that the IGM was heated above that adiabatic cooling limit, where the IGM would just be cooling from recombination all the way to redshift 7.9, and we can say that is not the case. And the reason we can say that is because if the spin temperature is very low, if it's just cooling adiabatically, this term 1 minus TCMB over TS will be quite large and negative, which will create a large amplitude power spectrum, which we don't see. So we could rule out the coldest models of reionization. Likewise, because we're doing this whole big parameter inference, we can say something about the X-ray luminosity per unit star formation rate during in this model for how X-rays are formed, and the IGM got heated. And if, as we believe, that heating is dominated at high redshift by high mass X-ray binaries, then this favors a low metallicity set of high mass X-ray binaries that look quite different from the modern day ones, where the due to losses driven by mass losses by line-driven winds, because at higher metallicity, these are a little bit less efficient in their X-ray production. So we are seeing evidence, though still tentative, that it is our data are more consistent with low metallicity high mass X-ray binaries than local analogs. So we did this not just in the context of 21 centimeter MC, but also in 3 other different models of modeling reionization of varying levels of complexity, which I'd be happy to get into if folks are curious. But we can use all of them to get roughly consistent results, which is that the IGM was definitely heated above the adiabatic cooling limit at redshift of 8 or so. Unclear whether it was heated above at redshift 10, which is the other band in which we made our measurements. So it's sort of in tension with those local analogs, but it's easily explained by low metallicity high mass X-ray binaries. We're also showing here the results from edges in Saros shown in the plane of T-spin over T-radio, and sort of range that would be explained by the edges signal and the tension that exists between these. So here's the edges 95% confidence interval and the Saros 2 sigma limit, and they're not totally, edges is not totally ruled out here, but there is some tension. And you could explain edges and HERA by an IGM that is cooled by null charged dark matter and then heated by high mass X-ray binaries. And in fact, edges, in order to explain it, also need some heating around redshift 14 or so. So, what's next for HERA? After these first limits that we put out, we sort of had a framework by which we could use those same techniques and just apply more data. So the simplest answer is just use more data to get a better measurement. So our current limits, as I mentioned, are from 18 nights of data, but we have a full season of data from what we called HERA phase 1. I'll get into phase 2 in a second, which we then split into a variety of epochs to analyze. And so after looking through hundreds of Jupyter notebooks to assess the quality of each particular night and the various systematics and what was good and what wasn't, we've got, at the end, 94 good nights of data with roughly a similar number of antennas as that first analysis. But now a full season. So we're spanning a huge range of RA or local sidereal time, depending on how you want to think about it, with considerably more depth. And so with those 94 nights, we can go through the entire analysis chain and we can form power spectra. And again, things are looking pretty good outside of the wedge plus some buffer, which is fairly standard in the literature. So I'm not at liberty to share the results quite yet. So I've blocked out the color bar, but things are looking pretty good. So with that, the next step is, of course, to run through all of our end-to-end simulations and our statistical tests and our jackknives, and, of course, the full astrophysical inference and interpretation machinery with these 4 different models. And we've actually done all that, and I'm writing it all up now. So we're in internal collaboration review, and I hope by the end of the summer we'll have something to share with the broader community. But I'll tease a little bit by saying, first off, that just from pure sensitivity, this could be as much as 3 times deeper than the previous HERA limit. And with a full season, we'll be able to say, hopefully, some interesting things about reionization and the X-ray heating of the intergalactic medium. So most of these sort of cold reionization models with dramatically enhanced power spectra should be ruled out by these kinds of things, assuming we're not making a detection. And of course, that means that we should also be able to show that the intergalactic medium was X-ray heated not just at redshift of 8 or so, but at redshift of 10 or so. And lastly, I think we'll be able to say something about those high mass X-ray binaries that probably heated the intergalactic medium, and that likely we'll be able to make a more definitive statement about their metallicity. So, while all of that is going on, we have, of course, not just resting on our laurels with the data set we took back in 2018. We're continuing to build out the full array all the way out to 350 antennas, which we've made tremendous progress in. So here's a more recent picture of HERA on the ground. And everything in the array is new, except the dishes themselves. So in particular, the correlator has been replaced, and the receivers and all the analog and digital electronics. But most importantly, we have new feeds, these Vivaldi feeds that I'm showing here, which are much wider bandwidth than the original feeds we used. So they should, in principle, let us go from 50 to 250 megahertz of redshift 4.7 to 29, which is a pretty big difference. And so that should allow us, if we can get a full season of sensitivity with a full array, we should easily have plenty of sensitivity both to detect the 21 centimeter brightness temperature at redshift 8 or so, the power spectrum at redshift 8 or so in both a standard scenario and kind of a more exotic scenario that might explain edges. But also, if edges is real, we should have tons of signal to noise at the relevant redshifts, redshift 17 or so, to really be able to rule that in or out. So we'll have plenty of additional signal to noise to play with as we mitigate our systematics. That HERA was designed to really knock this out and really not just detect, but also begin to characterize the 21 centimeter signal. And one of the upshots of that is that we should be able to really precisely pin down the ionization history of the universe. So we have some sense of how this went on from the cosmic microwave background. We have that integral constraint on tau, and then we have a number of somewhat model-dependent constraints from galaxy work and from quasar spectroscopy. But there's still a pretty large range of possible reionization scenarios that are not quite ruled out yet. And HERA, here we're showing the kinds of error bars we might expect, assuming this was the particular reionization history of the universe, which of course we don't know, but this is where HERA might be able to get us. And with that kind of constraint, we should be able to effectively eliminate tau as a CMB nuisance parameter. In the CMB, tau is degenerate, as many of you know, with a sub s the amplitude of scalar fluctuations from presumably inflation. And if we can eliminate tau, we can do a much better job measuring a sub s or equivalently sigma 8. And likewise, there's a degeneracy between tau and the sum of the neutrino masses. So we can eliminate tau as a nuisance parameter for the CMB. We should actually, with something like CMB S4, be able to make a much higher significance detection of the non-zero sum of the neutrino masses, which would be particularly exciting because we might be able to say something then about the hierarchy of the neutrinos. And of course, beyond just tau and helping out our friends across cosmology, there's a lot of interesting astrophysics to explore as we push to higher and higher redshifts beyond reionization, even if edges turns out to be wrong. Even if edges is wrong, there's still interesting astrophysics going on at redshift 17. And in particular, there's this complex interplay of reionization astrophysics and X-ray heating and cosmological parameters, and we should be able to constrain those things, many of which are currently unconstrained by orders of magnitude, quite well with HERA, as we showed in an example here, building an emulator on top of 21 cm fast to do this kind of thing. And in the slightly longer term, with just a few years of HERA observation, we should be able to actually detect velocity acoustic oscillations. So these are acoustic oscillations imprinted on the 21 centimeter signal via the differential impact on star formation of the relative velocity of baryons to dark matter. And where those velocities are larger or smaller, you can delay star formation in a way that creates this pretty robust statistical signal, this velocity acoustic oscillations, which are really interesting at redshift 16 because now we're talking about a potential standard ruler at redshift 16, which is kind of the geometric mean between the CMB and supernovae, and should give a totally independent handle on the distance ladder at a redshift that we've never been able to do before, and so may say something about the Hubble tension, which I think would be really exciting. Beyond HERA, and here I'm going to get a little bit more speculative, I think one thing to say about HERA is that it is the easiest path to having a really high SNR detection and being able to characterize the 21 centimeter power spectrum, but it is not the right instrument for building, for making the sort of ultimate maps of the universe that I alluded to at the beginning of my talk. And I think something not like HERA, but with a much larger array of smaller, simpler, easier to model elements is going to be the future of the field. And there's a challenge here. The challenge is going back to where we talked about visibilities, is in how we actually measure our visibility. So I mentioned visibilities are measured with every pair of antennas. So what we do is we measure the voltage at each antenna, we Fourier transform that in time, and then we cross-correlate every pair of antennas to form our visibilities. So we take those Fourier transforms and we average them down. That's the visibility that we're measuring at each point. And unfortunately, this scales like O of n squared. So if you double the number of antennas, you're going to need to quadruple the amount of processing. And eventually, the correlator becomes the most expensive part of the telescope. So how do we get around this? We get around this by using a fact which I think is quite beautiful and profound, even if it sounds a little glib, which is that all telescopes are Fourier transformers. And the way to think about this is as follows. So normally we think about a telescope, here's a telescope you're probably much more familiar with, as a device that converts angles on the sky to positions on the focal plane. And you can put this in a slightly more suggestive language if you've taken quantum mechanics, which is it's a device that converts photon momenta to positions on a focal plane. And the relationship between momentum and position is, of course, a Fourier transform. So if you think about rewriting this visibility equation in terms of the Fourier transform voltages, it can be rewritten suggestively in a way that looks an awful lot like a Fourier transform. And in particular, if your antenna's positions are on a regular grid or a hierarchically regular grid, effectively what you can do is you can directly sample that electric field, you Fourier transform, or you really use an FFT, and you can do that instead of O of n, you could do, or n is a number of antennas, you could do it in O of n log n. All of a sudden, the correlator is no longer the most expensive part because n log n is so much slower than n squared in terms of the growth of cost. So this is what we mean by an FFT telescope, a telescope that uses this kind of technique to achieve very large collecting areas. Now, I don't think it's going to look like HERA, but an FFT telescope can be much, much bigger than HERA. And that's the kind of thing that I think we want to be thinking forward to. It's not going to be we're not going to fill the horizon with HERA dishes, but we're going to want to build a telescope that's truly massive once we fully understand these systematics. So we know that an FFT telescope like this is going to need to be coplanar. It'll be need to be made up of really identical elements, otherwise you'll get the EOR window contamination we talked about before, and there's really no way around that. It'll have to be on either a regular or hierarchically regular grid, and actually HERA is an example of one that does that, so it can be a test bed for this, though it's not designed primarily to be an FFT telescope. And it also needs to be calibrated in real time. The reason why you're saving processing time is you're combining visibilities together that are measuring the same modes on the sky effectively. And if they're not calibrated, you're combining nonsense with nonsense and you get nonsense. So you have to be able to calibrate this thing in real time in order to integrate down. And that kind of real-time calibration is precisely what I believe that redundant calibration is going to be the key technology for that, because redundant calibration lets you do that relative calibration, so you can do that data compression in real time and build antennas not just with hundreds of elements, but tens of thousands or hundreds of thousands. And that's the kind of long-term future of the field. So we've showed that redundant calibration itself can be sped up from sort of a naive technique, which scales as O of n cubed with a number of antennas to more like O of n squared. And we've actually showed how you can use a subset of that data to achieve good enough answers, so sort of calibration errors that are below the noise level, with just an O of n log n subset of that. We explored different strategies for doing that in this paper. But the exciting thing, I think, is that this is the kind of technology that in the long term will enable us to map the majority of the volume of the observable universe, as I talked about before. And that'll allow us to do a lot of really interesting physics. So, for example, if you have direct measurements of small-scale density fluctuations, especially at early times, this can tell you about the nature of dark matter. If it's warm, that will affect the power spectrum. You can look for tests of inflation via non-Gaussianity, etc. So just measuring, opening up different scales that we haven't observed before and let us do interesting physics and cosmology. And likewise, because the intergalactic medium, especially before the first stars and galaxies turn on, is this effectively like a thermometer, and if we can measure the thermal history and its fluctuations, we might be able to say something about, for example, if dark matter was doing something other than just sitting there and collapsing under its own gravity, if it was annihilating or decaying, or if some fraction of dark matter is primordial black holes and they're evaporating, all of those things will have some impact on intergalactic medium and heat it, and it'd be inconsistent with other models of astrophysics that are going on later. And if we could see that effect, we could learn a lot about the nature of dark matter. And just because we have this giant volume, we can also do much finer kinds of constraints on the standard model of cosmology. We can measure our cosmological parameters to exquisite precision, and more importantly, we can really test our model, our lambda CDM model, by seeing whether things still work at these when you get to this level of precision. And that's the kind of thing that is almost unique for 21 centimeter in the far future, that this is the way that we can push beyond the cosmic microwave background and galaxy surface. And this is how we can get closer to a cosmic variance limited measurement of the universe. So To sum up, 21 centimeter cosmology, I believe, promises to be one of the premier probes of the high redshift universe, of our cosmic dawn and of reionization. But there are a lot of challenges. Foregrounds and other systematics are really tough, and we're dealing with a factor of 10 to the 5 times difference between the brightness of the foregrounds and the brightness of the signal we're looking for. And different telescopes have taken very different approaches to overcoming these, but HERA has really focused on the managed ignorance approach, this really robust, trading off some sensitivity, trading off the ability to make great images, because it's really a compact array with not a lot of angular resolution, for a robustness into this measurement. So we've set a world-leading upper limit now with just 18 nights of data and a very conservative analysis. And as I've alluded to, a lot more data is coming down the pipe. So that will, in time, as we build out to the full HERA and commission the array and get it and use the full power of this instrument, we should really be able to not just detect the 21 centimeter power spectrum, but really constrain the astrophysics of reionization, say something about the edge of signal, and in time, as we start thinking about next generation instruments that use this FFT technology, really test our models of cosmology and build some of the biggest ever 3D maps of our universe. So with that, thank you so much, and I look forward to your questions.